Today's presentation is about Lidar technology. Now, Lidar is an acronym for Light Detection and Ranging, a remote sensing method that uses light in the form of a pulsed laser to measure ranges or variable distances to the Earth. These light pulses, combined with other data recorded by the airborne system, generate precise three-dimensional information about the shape of the Earth and its surface characteristics. Now, I recently saw a program on TV where ancient lost cities were uncovered with LiDAR technology. It's amazing, Jeff. It is really amazing. But there is much more to LiDAR than that. So to tell us about the different applications of LiDAR, I'm very pleased to have Norman Banks with us. Norman used to be a registered professional land surveyor. He worked for Eskom in the department responsible for selecting and surveying routes for new power lines. In the mid-1990s, he formed a part of a team which conceptualized and developed the world's first combined airborne LiDAR and digital camera system. This team eventually left Eskom in 2006 to form a specialized aerial survey company, which is called Southern Mapping Company, to provide these services to a wider client base. From 2012, Norman served as CEO of the Southern Mapping Company. Since June this year, Norman has been semi-retired and is pursuing his own interests in the broad field of geospatial information science. Welcome again, Norman. We look forward to learn about LiDAR, and over to you.
Lovely. Johan, thank you very much for that great introduction. I think I'll enter a few things. Okay, I've got a presentation here, so I'll just share my screen so that we can get going. Are you seeing the presentation?
Yes, I can see it. It's not in presentation mode yet, but we can see it.
Okay,
yes.
Do we have...
Perfect.
Okay. Lovely stuff. Well, good morning, everybody. Thank you very much for the opportunity to come and chat to you. As Johan has said, remote sensing and LiDAR are amazing technologies, and they have uses across a wide variety of market verticals. And I'm sure I'll touch on market verticals that you folk have been involved in your active careers. I am quite happy, and in fact, I prefer it to treat this as a discussion as opposed to a lecture. So if anybody wants to ask a question while something is up, while a particular slide is up on the screen, please do so through Johan, and then we can chat about it while it's still fresh, rather than you listen to me drone on for 40 minutes, which is very boring.
Yes, Norman, sorry, I forgot to mention that. Norman asked me a few times that he likes the interactive questions. So please, if you have a question at a specific point in the presentation, either interrupt or just post it in the chat panel. And I'll put it to Norman. Thanks, Norman.
Cool, thanks. So the way this invitation worked is, as Johan mentioned, he saw this article on LiDAR for basically for archaeology, specifically Iron Age settlements in South Africa. And when Johan and I started chatting, I did mention that there's a lot of other stuff that LiDAR is used for. So he gave me permission to broaden the presentation slightly. So I will still focus on Iron Age settlements, which truly is fascinating. But I'll also indicate a couple of other things just in a couple of slides. And I'll start with a bit of an introduction into the whole topic of remote sensing in general and LiDAR in particular. So what is this term remote sensing? It's quite simply, it's the act of collecting information from a distance, and that could be anything. Measuring the distance or the length of a desk with a ruler is not remote sensing, because you're actually touching the object you're measuring. Anytime you're doing any kind of observation of an element or an object from a distance, you are doing remote sensing. And you can do that from a satellite. The weather satellites that we see every night on the news, that's a form of remote sensing. You can do it from an airborne platform. That airborne platform could be a manned aircraft, or more recently an unmanned aircraft or a drone. And you can do it from the ground. Those folk you see standing on the side of the road with an instrument mounted on a tripod, they're effectively doing remote sensing. And then that little lawnmower thingy you see on the bottom left of the screen at the moment, that's a ground penetrating radar device. That's measuring under the ground without digging in the ground. So it's showing us stuff, what information as to what is under the ground without us having to excavate. So how do we do this? And I apologize if I get a little bit technical from time to time. This is a slide of the electromagnetic spectrum, going from about a 100,000th of a nanometer on the left-hand side, which is a very, very short wavelength, of course, to about 1,000 or 10,000 kilometer wavelength waves on the right-hand side. And you will see that little colored in section in the middle, that is the visible spectrum, what our vast, woefully inadequate eyes can detect. And the gray is the infrared spectrum, and I'm sure all of you have seen infrared images from time to time. What I'm going to look at today, just very briefly, are some of these technologies. So you can see there's sonar technology, or technology that uses sonar to measure distances. There's radar, that's around about the 1 meter wavelength. That's the same kind of wavelength as you will as is used for radio waves. If we blow up or expand the visible and infrared section, you see things like visible imagery, you see hyperspectral, you see thermal, and you see Lidar, and I'll explain each of those in turn. And the combination of all of those various wavelengths allow us to see different things if we use different instruments focused on those different wavelengths. So what you get out of a radar wave is vastly different from what you get out of a thermal camera or a hyperspectral sensor. And that's where the fun really starts. So let's start with satellites. If you look at the two images on the right-hand side there, the upper one is a stock standard natural color image taken from a satellite, and that corresponds with what our eyes can see. If you look at the image over exactly the same area below, it looks different. Apart from the fact that it's grayscale, it's actually showing different information. You can see that circle with the line sticking up to the right. That's a completely different feature that's really not visible in the image above. So that might be a difference in soil, or it might be a brick structure, or it might be a difference in vegetation. It could be any number of things. And with experience and with what we call ground truthing, getting your boots on the ground and going looking at it, you can detect the difference, and you can build up a very rich identification or very rich map of the area, showing things that are truly invisible to the naked eye. On the bottom left, you will see what I think is a very pretty picture. That's called an interferogram, and that is that uses radar technology from satellite to measure movement of an object on the Earth. Radar, satellite-based radar, is something that I regard as close to a miracle as it's possible to be. If you do a simple measurement of using radar, it's not terribly accurate. So you'll get an elevation model that is accurate to maybe 5 to 10 meters if you're lucky. But if you instruct that satellite to return a second time and measure the same area, it can measure the difference between the first time and the second time to an accuracy of well under a centimeter. And that blows my tiny mind. I don't know about you guys, but that's quite spectacular. And it's used for things like settlement, subsidence monitoring, for movement of dam walls over time. It's used if you build a new dam or some infrastructure to see how what you have done has affected the natural ground level. And it's also used for things like earthquakes and volcanic eruptions to see what's changed from before to after. So very, very interesting and very detailed information that you can get out of a radar sensor. Carrying on, if we look at some of the technologies that are mounted on airborne platforms, you get what we sometimes call RGB. That's just an acronym for red, green, blue. So that's corresponding to what we see with our naked eye, or multispectral, which either breaks up the visible spectrum into very thin slices of light, so that you can look at things that are just in simple terms, dark red and light red differently, and you can discriminate between different elements there that have got different what we call signatures. And the difference between multispectral and hyperspectral is simply a multispectral sensor will have maybe up to 10 different slices of the of light being returned or measured, and hyperspectral will have up to 400 to 500 of these, very, very narrow, and going quite a long way out of the visible spectrum into the non-visible spectrum, or what we call the near infrared. That's if you think back to that chart of the electromagnetic spectrum that I showed, off to the right into that grey block called infrared. And an example of that is the image on the bottom left. That is a hyperspectral image of a rehabilitated minder. So what you're seeing there is anything that is that's showing up as green means there's healthy vegetation. We're focusing on vegetation in this instance because we're looking at the rehab. And anything that shows up as yellow is sort of okay. Anything that shows up as red, well, the vegetation has not really taken hold, and it's and there's a problem there. So,
can I interrupt there? I've got two questions here, and if you feel you will answer it in time during the presentation, you can just say so. Well, the first one is just a comment to say Peter Southwood is interested in coastal applications through seawater, but I'm sure you'll get to that. But the more other question from Anne, could this sort of thing have saved the disasters in KwaZulu-Natal in terms of the landslips, if done in good time?
Yeah, that's a great question. And I had no intention of dealing with either of those, so let me just chat about them both quickly. In terms of seawater, absolutely. It is possible to detect variations in salinity using a combination of these technologies. And it's also, obviously, because the very next element that I'm going to mention is thermal. It's possible to measure the difference in temperature of bodies of water within the bodies. So if you were to do this, for argument's sake, just off the coast at Kuberg down in the Western Cape, the nuclear power station, you would see temperature variations in the water. And you could use that to determine how the water that is being fed out from the power station is dispersing across the ocean. You can obviously also use that to look at estuaries and lagoons. You can measure differences in temperature between the rivers and seawater. You can see how the mixing is taking place, and again, how the dispersion is taking place using or by virtue of the ocean tides and the ocean currents. So very much so, you can measure salinity and temperature and probably other elements of water bodies. You can also measure turbidity, and you can measure the aspects of the chemical composition using hyperspectral technology. So you can look at clear water versus more turbid water. So you can use that for rivers to determine the pristineness, if you like, of the rivers. And it's also possible to do things like acid mine drainage. You can pick up the amount of dissolved minerals in a body of water, and to an extent you can also identify the types of minerals that are in that water. So yes, there's loads you can do with water, and that's probably deserving of a lecture all on its own. In terms of the landslips, my sense is that no, not really, because that was sort of a catastrophic event, in that there was, I must apologize if you're hearing my dogs protecting me. It was a catastrophic event in that it happened over a period of just a few days. But it is used extensively for monitoring of land that is considered to be vulnerable to landslides. And in those circumstances, you can detect slips of actually quite small extents, probably in the order of around about a centimeter, certainly less than a decimeter. And I mentioned earlier on that for something like a concrete dam wall, it is trivial to measure these kind of movements. For earth dam walls, it is also possible to do so. So it can be used for early prediction. And I think a lot of you will be aware of the various tailings dams failures that have been experienced around the world over the last few years. And going all the way back to the Mariesspruit one in South Africa in I think it was the 70s or the 80s. All of those could have been identified well in advance if people had been using these technologies. In addition to that, Lynn, the sinkholes that we've experienced in places like Carletonville and Pretoria could also, some of them could also have been predicted and not necessarily prevented, but certainly we could have minimized damage and loss of life if these kind of technologies had been used in advance of those failures. I hope that answers the two questions, Johan.
I think there's just one follow-up on that. How deep does LiDAR work through water?
There's a thing called a Secchi depth, and if you take a disc that is about 30 centimeters in diameter and lower it into the water, at some stage you will not be able to see that with your naked eye anymore. A LiDAR can penetrate between 2 and 3 times further than that. So if you can see down to a meter, LiDAR will get 2 to 3 meters. In the river water of South Africa, well, that means you can probably get a couple of centimeters of LiDAR penetration. Because our water is quite dirty. It's not called the Vaal and the Orange for nothing. But if you go to places like the Great Barrier Reef or the Red Sea, they are successfully using airborne LiDAR taken from a kilometer above the water surface to measure distances of 50 to 70 meters below the surface of the water. So it is a very effective technology for measuring, for doing bathymetric surveys in the right parts of the world where the water is nice and clear.
Great, thanks, Norman.
Okay. All right, so we were talking about the RGB, the multispectral, the hyperspectral. We were looking at the image on the bottom left. If you look at the image in the middle, that pretty purple and white image, that is a thermal image of a coal dump in Mpumalanga. And those white arcs that you are seeing are underground burning of the coal. And so thermal can use this, is actually measuring surface temperature to indicate what is going on under the surface of a coal dump. And we've used that very successfully, both for dumps and for underground mines, shallow underground mines, to determine where some sort of combustion is happening in the coal fields. Thermal is also used for measuring or for detecting groundwater. You can see an underground stream or an underground body of water if you do the surveys early in the morning between, say, midnight and sunrise. You get very, very good imagery showing groundwater. And a couple of years ago, that Southern Mapping Company where I worked, we did a survey of the area between Pilanesberg and Tabazimbi up in the Northwest Province, where we were using this thermal survey to look for groundwater for optimal drilling of boreholes for agricultural land, and it worked quite successfully. The next element that's on this page is Lidar, and what that pretty picture, the big picture on the right, is a terrain model of one of the dams in Lesotho before it was inundated, and that is a Lidar elevation model showing the terrain, and obviously blue is low, showing the water courses, and red is high, showing the hills. And then I'm not going to get into this topic at all, but remote sensing, I did mention it can be used at ground level. What we're seeing there is from the right to the left is a tripod-mounted laser scanner, very effectively used inside buildings to do as-built surveys of plants, like mine process plants or factories. In the middle is a hyperspectral spectrometer. You use that to identify vegetation or soil types or metal types or precious stones, things like that. And there's that lawnmower type thing, the ground penetrating radar again. That's for determining pipes and electrical conduit underground. You also use ground penetrating radar for other things, and it's used fairly extensively in the archaeological space, and I've got a couple of slides on that later. So, getting to the acronyms, Johan's already told you what laser is. Thank you very much, Johan. The next three are a family of acronyms. All of you will be familiar with radar and sonar. Those came into our consciousness around about the Second World War era. Sonar is primarily used for measuring distances in water. Radar is used for measuring distances through the air, and Lidar is also used for measuring distances through the air. And the difference is sonar uses sound waves, radar uses radio frequency waves, and Lidar uses light frequency waves. Each one of those comes with their advantages and disadvantages. And prime amongst them is accuracy. The shorter the wavelength, the more accurate you can get it. So in order from Lidar has the shortest wavelength at round about 1,000 nanometers or a tenth of a millimeter. A thousandth of a millimeter rather. Sonar is round about just less than a tenth of a millimeter, and radar is in the decimeter to meter range, and those accuracies then derive as a result of that. And I've mentioned the GPR before as ground penetrating radar. So it's also using radar, but at a particular wavelength that allows it to penetrate through the ground. Some wavelengths will penetrate, some wavelengths will reflect off the first thing they hit. So one uses different instruments for different purposes. So what is a LiDAR system? From an airborne point of view, it requires some sort of an aerial platform, and that can be a manned aircraft, a helicopter, or a drone. It requires a GPS technology. I'm assuming everybody's familiar with GPS. We all have it on our phones and our watches these days. It is not accurate enough for survey quality to have it in an aircraft that's traveling at 200 kilometers an hour. So we add another GPS on the ground at the same time, and we measure the differences between those two GPS receivers, and that gives us in the order of 5 centimeter accuracy position of our aircraft. So at all times now, we know where our aircraft is to an accuracy of around about 5 centimeters. We then add an inertial system to that, and that measures how the aircraft is moving in space. Obviously, it can't travel nice and smoothly, flat and level. So we measure the way the aircraft rolls, pitches, and yaws. We measure that 200 times a second. We also measure the way the aircraft, the speed that the aircraft is moving using that system. And then we combine the GPS and that inertial system information to improve the accuracy of the position of the aircraft as well as the way it's pointing. Once you know where the aircraft is and where it's pointing, you've now got a position from where your laser is sending out its pulses. When we bought our first system back in 1996, it could measure 5,000 pulses every second, which was pretty remarkable in my eyes. Now, modern systems measure up to 2 million of those pulses every second. And what happens, it's just sending out a beam of light that reflects off something, and it reflects back to the aircraft. And it measures the time it takes to go out and come back, and it converts that to a distance using the speed of light. And then once we've got that, we also have a camera, and we take images as we go along, overlapping images, so that we can put together a continuous orthophoto map, is what we call it, of the area under consideration. The kind of accuracies that you get out of such a survey are very much dependent on the height that you're flying. So if you put that in a drone, you're not going to cover a large area in a day, but you're going to get accuracies in the order of 2 to 3 centimeters of your elevation or of whatever you're measuring. You're going to get very, very high point densities, so that allows you to do very accurate changes of elevation within a meter. You're going to get a very high image resolution, but you're not going to get a great coverage. And as you go higher, the accuracies obviously decrease, the coverages decrease, the resolution decrease, but the amount of area that you cover increases. So it all depends on why do you want to do the survey and what information are you trying to extract, and critically, how much money you've got. The lower you go, the more it costs you. Why would you want to use LiDAR? This is a path or a road through the tropical forests of Gabon. We did a survey up there a few years ago, and you can see that's pretty dense vegetation. And there's no ways using a normal camera that you're going to be able to see through to ground level. But if you look at that strip at the bottom, that is a side view of the white line that I've drawn in the top-down image above. The dots that you see that are colored green are actually where the laser has hit a tree or part of an above-ground element and reflected back. Where you see a brown dot, that is where it's got through to the ground. And you can see that this laser, because it's got a very narrow pulse, it goes through all of those gaps in the vegetation that we can't see with our eye. It gets through the ground and critically gets back out again, back up to the aircraft, and we're able to measure the elevation of a ground point. So no other technology is able to do that. It has all sorts of implications for surveying without having to clear vegetation from the potential mapping area. And that has huge environmental benefits, of course. The other major reason why Lidar is a great technology is that it, again, uniquely has the ability to measure above the ground. So what you see there is a substation somewhere in South Africa. That top insert that you see is along the line of a power line, and you can see the towers and the conductors. Those conductors are small. They are in the order of the big ones that actually conduct electricity on the order of a couple of centimeters in diameter at most. And the earth wires that protect the conductor and the towers above are about a centimeter or less in diameter. So they are very, very small. And to be able to pick those up is basically remarkable. So those are the two main reasons why one would use LiDAR technology. It's also significantly faster to capture and process than conventional aerial photography. So just in summary, before we get onto the pretty pictures, why would we use remote sensing? It gives you a big picture view. It allows you to cover large areas rapidly, and it provides information that you just can't get efficiently on the ground, or that it's impossible to get on the ground. It also allows you to capture all of the varieties of technology that I've been droning on about today, and allows you to combine them. And truly, we will always like to say that when you're adding data sets like this, the thermal and the visible and the elevation, 1 + 1 doesn't equal 2 anymore, it equals 3 or 4. The richness of the information set that you're able to build up is just spectacular. So I'm going to start with what I've called here LiDAR for other stuff. That means non-archaeology. So I'm going to talk about mining. I'm going to talk about infrastructure, just very, very briefly. So mining, this is, for those of you who might have spent time in the mining industry in Botswana, this is the Orapa mine, or sorry, the Letlhakane mine up in Botswana. It is a diamond mine, and diamond mines are typically characterized as diamonds are extracted from kimberlites, and the kimberlites are very circular in nature. And this pit is almost perfectly circular. It's quite a spectacular view. What you're seeing there in the middle is the elevation model derived from the LiDAR, and that allows us to extract all sorts of information. So we can determine the volume of that pit. We can determine how that volume has changed since the last time. We can determine the volume of the stockpiles. We can determine how those have grown over time. We can have a look at the slimes dams, and we can see, are they getting too close to the top of the walls? Is there a danger of them overtopping? Is there a danger of them actually failing? And you can use all of that, all of the LiDAR information to answer those kind of straightforward day-to-day operational questions. If you have a look at the bottom, that is a side view of a stockpile being fed. The green diagonal set of lines, that is a spreader taking a conveyor on a structure, taking the waste to a stockpile. And that again can be used. You can measure the volume of that stockpile almost trivially in a matter of seconds. To measure that stockpile using a surveyor on the ground would take a good couple of hours. Moving on to power lines. This is a power line down in KwaZulu-Natal. You can see the imagery on the left. You can see the LiDAR on the right. And again, you can see the side view showing the power line at the bottom. And where this becomes incredibly valuable is you can measure the distance from the conductors to the ground. You can measure the distance from the conductors to the top of vegetation. And if those go, if those are not far enough apart, then you have a danger of a flashover. People can be electrocuted, or a fire could start, or it could just short. So you need to know that. And this was, in fact, the use case that we proposed to Eskom back in 1996 to allow us to acquire this technology. And it was used extremely effectively to do as-built surveys of many of the power lines around South Africa, determine where there are underclearances, and which allows then the engineers to design mitigation measures. This is the Kendall Power Station, again showing the above ground richness of information that's been captured. And you can imagine you can do an extremely detailed as-built survey of this. Moving on to dams. This is the Kambembe Dam up in Angola. And what they wanted to do was determine the capacity for elevating the dam wall and how much extra water volume would they be able to contain. So we did a survey. You can see the smoothness where the river course is on the top left image. That's the existing water. On the top right, you can see a nice visualization of the imagery draped over that 3D model. Then at the bottom, you can see a green line indicating the current full supply level, taken from the contour line of the top of the dam. And on the right-hand side, you can see a new full supply level if we were to increase the height of the dam wall by X number of meters. I forget exactly how many meters they were talking about, possibly about 5 or 10 meters that they wanted to raise the dam wall. And that allowed us to work out that there'd be X more million cubic meters that they could capture by raising the dam wall. And we were able to do that in a very straightforward manner. So those are just a couple of quick examples that I wanted to show you other potential uses for LiDAR. Getting on now to LiDAR for archaeology. What you're seeing there is an image of LiDAR where the above ground vegetation has been stripped away. If you think back to that forestry slide I showed you, you could see all of those green dots that showed the above ground vegetation. We've taken those out. We're only left with the brown dots. And what you can see there is a what we call a bare earth model with, critically, the very small walls that have left behind from the ruins of this Iron Age village. Iron Age in South Africa is characterized by a period roughly from 1500 to around about the late 1800s. And these would have been villages made of stone. The huts would typically be rondavels, and you can see very clearly the circular patterns there. And in many instances, these walls have either been repurposed, the rocks have been taken to be used for something else, or they've been vandalized, or they've simply just been allowed to decay. And in many instances, those walls that we're picking up there are 20 or 30 centimeters high only anymore, instead of the 1 to 2 meters high that they would have been while they were in use. It therefore becomes very difficult to identify these walls when they are pretty much not even protruding above the level of the grass. So the LiDAR technology gives us the ability to discriminate between the vegetation of the grass and the rocks, the remaining rocks of the wall. And here we've got an example. This is Kadachweni, just to the west of Pilanesberg. And just as a side, for those of you who've ever spent time in the Pilanesberg, there is a beautifully preserved Iron Age village that is available for you to walk through and explore in the Pilanesberg. And I would highly recommend, if you get a chance to get up there, I know it's a long way from Helderberg, to go and have a look at that. There are something like 100,000 of these villages scattered around Limpopo, Mpumalanga, Northwest, and the Northern Cape, as the various tribes moved around and as various successions happened. Typically, when a chief died, they would abandon the village and they would go and build a new village for the new chief. I guess that's like divorce these days, eh? Got to have a new house for the new wife. But what you can see there is some evidence of walls in the bare areas, but you really can't see what's going on to any great degree of certainty. So if we add the Lidar points, you can see now we've identified all of the walls in red. We've identified the vegetation in green, and you can start seeing what's happening there. If we take the vegetation layers away, again, you can see what I showed earlier on. You can start seeing the evidence of the walls, and you can, because the archaeologists understand the way these villages were laid out, they're able to work out which were sleeping quarters, which were cattle kraals, which were royal quarters, which were quarters for the chief's wives, and so on and so on, just by their size and location within the village. And there we can see standing out a little bit more clearly, and drawn over the image, you can start seeing what's going on and putting things together. If you have a look at this cross section, you can see that the walls in this instance are sticking out fairly nicely from the ground, but they're still only in the order of decimeters above the surface of the ground. This is a different site in the same area, a place called Pilwi, and there you can see, because of the vegetation there's precious little that you can determine from that image. But once we again take the Lidar class, strip away the vegetation, you can see on the right-hand side that the imagery is, or that the Lidar is showing up the walls, but a little bit faintly. If we enhance that by exaggerating the vertical differences, then it starts to stick out quite nicely. It becomes a bit noisy, but it does stick out, and you're able to start working out what's going on. And this is again some side elevations. This allows you to determine, to have a look and understand, interpret a little bit better. And this taking the wall sets and overlaying it on the vegetation. Again, it allows you to start figuring out what's happening. And there's just zooming in a little bit. Obviously, what happens over time is that as a village gets abandoned, there will be cow dung left behind. That cow dung will contain seeds of vegetation. So the village will tend to become overgrown quite densely as those seeds germinate and turn into different types of vegetation. Just changing focus a little bit, I mentioned that survey we did around the Pilanesberg area, looking for groundwater. What we did, we flew the area by day to get the imagery, and then we flew it again by night to do the thermal. And what you see here is evidence of villages using thermal technology. So we are using the principle that rocks cool more slowly at night than soil and vegetation. So you can see a very well preserved circle of huts, walls there. And that has enabled the archaeology folk at UNISA to understand the the layout and the location of these villages a little bit better. I mentioned that ground penetrating radar is used in archaeology. Unfortunately, I don't have any examples in a South African context, so we're going to have to go over to the UK, where they are excavating for Roman ruins there. And what you can see there are the various, those are different depth slices below the ground, and you can see the different walls of the building that has been buried in that image. And again, this is the same sort of thing. This is a village that is partially visible through visual clues, but it sticks out very nicely in a radar image, a ground penetrating radar image. I'm sure a lot of you get feeds from different news sources, and you will have seen that the droughts in Europe have shown up a lot of archaeological remains. And so this is a very exciting time when there's a drought, very exciting time for archaeologists, and they get out and they start poring over satellite imagery, and they start tramping around the bush looking for signs of ruins that are not evident in wetter areas. This is one of the great projects we did a few years ago. We surveyed Great Zimbabwe up in Zim. What you're seeing here is the hill that is looking over the actual main part of the Great Zimbabwe village. And you can see there in the various grey overlays are where there is wall structures to be found. This is what the elevation looks like. Great Zimbabwe itself is down to the bottom right, with some sort of settlement structures up on the top of the hill, and various other features along the valley. We were able to find some structures that they weren't initially aware of that stuck out, particularly drainage pits that had been partially filled in or partially eroded away. And this survey contributed to the understanding of the layout of the Great Zimbabwe area. This is just the entire Great Zimbabwe. We've created a little bit of a visualization. What you're seeing there on the left is the most well-preserved wall. Those walls are something like 2.5 meters to 3 meters high. And again, you can see how the vegetation has grown inside the walls because of the cattle and the dung and so on. Johan, that's pretty much what I've got. I hope that was interesting, and I'm quite happy to take questions now.
Norman, thank you very much. I can see you spent a lot of time to prepare this. I do have the two questions from Derek earlier, and just be warned, Derek is a very tech-savvy guy, so he's got maybe a loaded question. He's asking, what is available for the general public to utilize or experience the technology on LiDAR-enabled mobile devices? So with that, Derek told me something which I didn't know, that some of our current smartphones already has got LiDAR-enabled apps loaded onto them.
Okay.
And then maybe just his follow-up question, are there any conditions that prove to be a challenge for LiDAR or may render the technology unusable?
Okay. All right, two very different questions there, Derek. Let me answer the easy one first. Yes, LiDAR works in a lot of environments. And it does a lot of great things. It can work it works as well in the middle of the night as it does in the middle of the day, because it's what we call an active technology. Excuse me. pulse is actually sent out from the LiDAR and received back. So, as I say, it works as well at midnight as it does at midday. But its Achilles heel is moisture. So, if it's raining, well then we don't serve it. If it cannot survey through cloud for the same reason, clouds are essentially moisture. But apart from that, it is pretty much can be used at any time. It has range limitations. Some LiDAR systems can only measure in the order of 30 meters. Other LiDAR systems measure up to 6 kilometers. And the reasons for those, obviously they're designed for different purposes. A LiDAR system that measures 30 meters is always going to be mounted on a tripod, and it's used for very accurate but very short range purposes, like for monitoring of a dam wall movement. Along those lines, you get accuracies in the order of tenths of a millimeter with those kinds of sensors. As the distances get longer, so the accuracy reduces, and when you get to those 6 kilometer ranges, you're getting 20 to 40 centimeter vertical accuracies. So yeah, those are essentially the limitations of LiDAR. In terms of the LiDAR devices, I'm not that up to speed on them at the moment. They are, I do understand that some of the iPhones are starting to come out with them. But what all smartphones are able to do just by using a particular app is that you can do what we call structure for motion, and that entails taking a lot of photographs with your cell phone all around the element that you want to survey, and then it uses a technology called photogrammetry, which just entails, it just means making measurements from pictures, and it's a very long-standing survey technique. Has been used for 120, 130 years now, and these applications use photogrammetry to take those very simple photographs that you take with your cell phone camera and reconstruct a 3D visualization or 3D rendering of the image. And you could do that with your coffee cup or with a chair around the house or anything like that. So yes, your mobile devices now have become survey devices.
Norman, thank you. I see Derek did post in the chat box also a reference to especially the Apple smartphones with this LiDAR scanners built into them and what you can do to them.
Yeah.
Unfortunately, just due to this time restriction, I will have to cut it short. We've still got a few things to do from an admin point of view. But Norman, thank you very much. I'm so glad I came across you. And that's also another long story how I got to Norman. But I really appreciate your time and effort to present this. And for me, Jeff, it is amazing. You can go and watch on YouTube. There are some videos available on YouTube where they've uncovered lost cities and restructured it. It's really fascinating. But Norman, thanks for presenting to us down here in the Cape, and all the best up there in the north.